Imagine a storm so powerful it lights up the sky with breathtaking colors and disrupts our technology. Sounds like science fiction, right? But it's happening right now. Welcome to our exploration of the most intense solar storm in 20 years. This storm is not just a stunning light show. It could, in fact, have significant implications for our technology and daily lives. Recently, Elon Musk reported that his Starlink satellite service was really feeling the pressure from these solar storms. Although it's managing the pressure at the moment, it shows the real impact on our technology that these extreme space weather events can have on us. Let's break down what happened, how it affects us, and what we can expect in the future. The recent and ongoing 2024 solar storm, triggered by sunspots 16 times the size of Earth, unleashed powerful X-class solar flares and coronal mass ejections, or CMEs. These led to severe geomagnetic storms, reaching a G5 intensity level, the highest on the scale. Think of this like a Category 5 hurricane in space weather. So what exactly happened on the Sun's surface to cause this geomagnetic storm? And how does it create such stunning auroras visible 150 million kilometers away? The reason behind the recent solar storm is the sunspot group named AR3664. Sunspots are temporary dark areas on the Sun's surface, appearing darker because they are cooler than the surrounding areas. The temperature in the center of a sunspot is between 3,000 and 4,500 Kelvin, much cooler compared to the surrounding area's temperature of about 5,800 Kelvin. The AR3664 cluster rotated into view of Earth a few days ago. At that time, it looked fairly normal, but then it grew rapidly to become 16 times as wide as our planet, spanning 200,000 kilometers, equivalent to the entire distance from London to Sydney, and back again. It's become one of the largest sunspots of the current solar cycle. NOAA's Space Weather Prediction Center issued warnings of increased solar flare risk from AR3664 at the beginning of the month, and the dark patch on the Sun lived up to its expectations. AR3664 emitted a total of 75 M-class flares and 10 X-class flares within a week, accounting for 50% of the X-class flares this year. A solar flare is a sudden, localized, and intense burst of radiation on the Sun, resulting in a brilliant flash of light across various wavelengths. They can last from minutes to hours and contain tremendous amounts of energy. The light emitted from these flares reaches our planet in 8 minutes and 20 seconds. Flares are ranked by their strength. B class is the smallest, followed by C, M, and then X, the most significant. The scales differ in strength by a factor of 10. Each class is further divided into a scale from 1 to 9. C-class flares are generally too weak to affect Earth significantly. However, M-class flares can cause short-term radio blackouts at the poles and minor radiation storms, posing potential risks to astronauts. Most people get confused between a solar flare and a coronal mass ejection, or CME. A CME is an immense cloud of magnetized particles hurled into space from the Sun. These eruptions occur when the Sun's magnetic fields explosively realign, propelling solar matter into space. CMEs travel at speeds exceeding 1 million miles per hour and can take up to 3 days to reach Earth. Unlike solar flares, CMEs are massive fans of gas swelling into space. When a CME interacts with the Earth's magnetic fields, it creates currents that drive particles toward Earth's poles, leading to the formation of auroras. In summary, while both solar flares and CMEs are born from the Sun's magnetic field realignments, they emit different things, look different, travel differently, and have distinct effects on near planets like Earth. Solar flares manifest as bright flashes of light, while CMEs appear as enormous clouds of magnetized particles moving through space. The solar activity began to escalate on May 3rd with the observation of an X1.6 solar flare. Within the next 48 hours, 2 additional X-class flares were detected. However, the situation intensified the following day when the sunspot region emitted an even larger X4.5 flare, unleashing tremendous energy. The first coronal mass ejection was then observed departing from the Sun on May 6th. A couple of days later, on May 8th, another CME was spotted following an M8.6 flare. Then, on May 9th, 2 X-class flares resulted in 2 more CMEs. By May 10th, 4 CMEs were traveling toward Earth. Scientists believe the last 3 CMEs combined into a single larger event, known as a cannibal CME, due to their varying speeds and overlapping trajectories. When a CME reaches Earth, something interesting happens. The Earth's magnetic field deflects the solar storm. The magnetic fields couple together and create a funnel where the gas streams down on the day side of the pole. This results in the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and the gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora. Auroras are often thought of as green, but when they are especially energetic, they can light up the sky with huge red glows. The color differences are due to the types of particles involved and the altitudes where these interactions occur. Blue and purple auroras are seen when solar particles interact with molecular nitrogen up to 100 kilometers. That's about the cruising distance of a commercial aeroplane. Green auroras are created when these particles interact with oxygen at altitudes between 100 and 300 kilometers. However, the striking red auroras we sometimes see occur during intense solar storms when these interactions happen with oxygen at higher altitudes between 300 and 400 kilometers. Additionally, for red auroras to be visible to the naked eye, they must be at least 10 times brighter than the green auroras. Geomagnetic storms can have significant impacts on electrical power grids and satellite infrastructure. During a geomagnetic storm, geomagnetically induced currents, or GICs, can flow through power transmission lines and transformers. This can cause transformers to become saturated and overheat, leading to various electrical issues. Specifically, transformers may fail, protective equipment can trip, transmission lines might overload, and generators could be damaged. In severe cases, these issues can result in large-scale blackouts. An example of this occurred in 1989 in Quebec, Canada, where a geomagnetic storm left 6 million people without power for 9 hours. Then, in October 2003, the Halloween storms caused widespread satellite and communication disruptions, as well as power grid issues in Sweden. In 2022, a flare from the Sun resulted in the loss of 40 newly launched Starlink satellites. Currently, the sunspot group known as AR36664 has moved behind the Sun's disk, making it temporarily invisible from Earth. This means that any solar emissions from this group will not affect our planet for the next 2 weeks. However, AR36664 is expected to reappear and face Earth again in 2 weeks. Based on past behaviors observed in sunspots, there's a possibility that this group could remain active once it becomes visible again. Just before it rotated out of view on May 11th, AR36664 produced significant solar activity, including an X1.8 and a much larger X5.8 flare, the latter of which was associated with a CME. This activity suggests that AR3664 could still produce more solar flares in the future and indicates that its cycle of activity isn't over yet. AR3664 is no ordinary sunspot. It's so big that it can be seen from Earth without magnification. However, do not attempt to look at the Sun without a solar filter or eclipse glasses. The size of AR36664 is comparable to the sunspot that caused the Carrington event in 1859, the most intense geomagnetic storm on record. The storm associated with the Carrington event caused sparking and fires in telegraph stations, and auroras were visible as far south as the Caribbean and Mexico. In 1859, the most advanced electrical technology was the telegraph system. Today, however, our society heavily relies on satellites and various technologies that need stable magnetic environments to function correctly. This dependence makes us more vulnerable to the effects of significant solar activity, such as that exhibited by sunspots similar to AR 3664. The increased reliance on electricity and emerging technology in today's society means that any disruption could lead to trillions of dollars in monetary losses and pose risks to life dependent on these systems. The potential impact of a Carrington-class event today has been estimated to result in damages ranging from 0.6 to 2.6 trillion in the US alone. It is crucial to recognize the threat posed by extreme solar storms and take proactive measures to protect our technology and infrastructure against the potential devastation of such events. The solar storms of May 2024 hint that the solar maximum, along with the sun's magnetic field flip, may arrive sooner than we thought. For a deeper dive, check out our detailed video on the solar cycle and its impacts. If you found this video useful, drop us a like and a follow for more space content. And quickly, before you go, we want to let you know that you can now explore the wonders of the cosmos right at home with our brand new Cosmo Glow Astro Galaxy projector. It projects stunning, realistic images of the solar system, Earth, the Moon, and more. Click the link in the description to bring the universe to your room. See you in the next one, and until then, keep looking up and stay curious.